Okay, let's go over determination of limits. Okay, so let's say you're asked to determine the limit as x approaches 2 for x squared plus 2x. So how basically do you get to determine this limit? So whenever you've got a simple algebraic uh, expression such as that one, and then you are given a limit, so all you're trying to do is determine the value of this function when x is equal to that. So therefore this limit, we're going to have the limit as x approaches 2, where there's x we're going to put the 2, so we have 2 squared plus 2 and then 2, which gives us what? So if that is 4 plus 4, that is 8. Okay, so the limit is equal to 8. Okay, now let's make it a bit more interesting. Again, as you might guess, of course, even if we said negative 2, it doesn't matter what you have. Even if you add that and then a negative or even a positive x to the power 3, you can have all sorts of functions. You can have a linear function there. All you have to do is just do the same. Okay, that's the basic idea. So you just substitute again, you end up with a value of negative 5 if you put negative 2 as x. Okay, so with that basic understanding of determining a limit, how do you determine the limit as x approaches, let's say 1 for x squared minus 1 over x minus 1. Okay, so let's try to simplify this one. So obviously we expect that the limit as x approaches 1, we're going to have x squared minus 1. So now where there's x, we're going to put the 1. So we have 1 squared minus 1 over 1 minus 1. So we end up with 0 over 0. Now mathematically this is undefined. We can't determine that value. Why? Because we can't divide by the denominator of a 0. So how do we handle such questions now? So instead of just substituting directly for such expressions, ensure that the denominator should not be equal to 0. So in a case where you're given an expression where you're able to factorize the numerator, you're at an advantage. Okay, so how do we basically get to factorize the top part there? So we're going to have the limit as x approaches 1. We know that we can square 1, so that we have got the difference of 2 squares. The difference of 2 squares tells us that if you have it's a difference or a negative or a minus, depending on what you're going to call it yourself, and then you've got two things squared, what that tells you is you're going to have one is going to take the negative sign and then the other is going to take a positive sign. So you take away the square and then over x minus 1. So obviously, as you might guess, the two can divide. So you remain with the limit as x approaches 1 for x plus 1, which you can just now substitute now. Where there's x, you put a 1, and then it gives you what? It gives you 2. So that's another approach when it comes to the limit. So let's look at some more interesting questions. I can just modify the same one and make it more interesting. We see what's going to happen. What happens if I instead swapped what we have on the bottom and then I said 1 minus x? How do we handle that? So obviously we know if you put where there's x again, if you put a 1, you're going to get a 0. So pause the video and try this one out. So we'll do the same. The difference of 2 squares again on top. So we're going to have the limit as x approaches 1. So we have x minus 1 and then x plus 1. For the denominator we have 1 minus x. Now you can see that here you can't just cancel because these are two different things. Alright, so how do we do? So factor out a negative 1 on the bottom. So if you have to factorize a negative 1, the sign changes, it becomes x minus 1. Because the basic idea is if you multiply the negative 1 with whatever is in the brackets there, it takes you back to this form. Alright? So I can factorize the negative 1 on the bottom, and then we have x minus 1. And then this and that can divide. So we are now dividing by negative 1, which can just become the numerator. So the limit as x approaches 1, The negative 1 can just go on top, and then we have x plus 1. So where there is x, we can put the 1, right? And then we end up with a value of a negative 2. Interesting, right? Okay. I can give you several examples in the same manner which would involve a sum. Let's say the limit is x approaches negative 3, and then you have x squared plus x minus 6 over x plus 3. So you notice that this is not a difference of two squares, but all the same we're able to put a negative 3 and get a 0 on the denominator, which we don't want. So how do we handle it? So let's try to factorize the numerator. We see if we're able to. So negative, the product there we know is negative 6. The sum is 1, two numbers 3 and negative 2. So we have x plus 3, x minus 2. So how do we get the product? Get the coefficient of x squared and the constant c. The sum is the coefficient of the middle part. Okay. So we can substitute that. So we have the limit as x approaches negative 3, and then we have x plus 3, x minus 2. So if you multiply that, you're going to get the one that's on top, right? And then you've got x plus 3. So you can clearly see that as the same procedure. We can divide, and then you end up with the limit as x approaches negative 3. Where there's x, we're going to put negative 3, and then you have negative 3 minus 2, which is just equal to negative 5. Okay, so we've seen that it's not only the difference of two squares, but even just normal factorization, you should be able to apply the same concepts and answer different questions. You can look at the limit as x approaches 5 for x squared minus 25 over x squared plus x minus 30. You notice that this is also unique, yeah, but all the same, if you substitute, you're going to get to 0. Interestingly, you're going to get to 0. So how do you handle this one? We can try to factorize as well. You know the product for the denominator is negative 30. The sum is 1. What two numbers can you deal with? You can deal with 6 and negative 5. So, and then we also have a difference of two squares. So the factors are 6 and negative 5. So for the numerator, we're going to have the limit as x approaches 5. And then we have, so 25, for 25, that's like 5 squared, right? You can take it as 5 squared, so that you can have a difference of two squares. So we have x minus 5, x plus 5. For the denominator, we can apply the same concept, factorization of that. Whenever you've got a square of x, just substitute. So we're going to have x plus 6 and then x minus 5. Okay, we can clearly see this can divide at least what we have. So we now have the limit as x approaches 5. We have x plus 5 over x plus 6. At this point now we know we can substitute the value of 5, right? So I have 5 plus 5 over 5 plus 6. So I have 10 over 11. Okay. So you've seen you can have both now. You can apply both the difference of two squares and just normal factorization. As a limit, you can have such a limit as well. And you should be able to handle it with ease. Okay. Now let me give you one more interesting one. This same form. The limit as x approaches 2, x to the power 3 minus 8 over x minus 2. Now you notice that we are now dividing, and of course if we do substitute in the denominator, we're going to have something that's undefined. So how do we handle, or how do we determine this limit? So the basic idea here is you have to apply the same concept we've been applying of dividing this with what's on the top. But as you can see, we can't actually deal with the top part as a difference of two squares because we've got the power 3 instead. So let's apply the concept of long division. So let's divide by x minus 2. So x minus 2. So if you're new to long division, don't worry, I'm still going to explain just here. I'll show how. So we're dividing x minus 2. We're dividing x minus 2 into x to the power 3 minus 8. Now the basic idea is instead of you just saying minus 8, you have to indicate it all the way as it reduces to minus 8, which is a constant. So we'll add imaginary parts. We know from x to the power 3 we have the power 2, and then to a power 1, and then finally a constant. So you can see that the middle part, 0x squared and 0x, are imaginary to just help us perform calculations. You see why. So what we do is divide by the x. So divide that into that, you're going to have x squared, and then multiply the x squared with the entire part here. So times x is x cubed, times the minus 2 is minus 2x squared. And then we subtract, so you end up with a positive 2x squared. And then of course divide, we have a 2. So we're dividing the x into that. So we have a 2x. And then again multiply with the entire part there. You have 2x and then minus 4x. And then subtract again. So here we have 0x, subtract, you get a positive 4x. Again multiply, divide, sorry, this into that. We have 4. And then 4x minus 8. Minus 8. And then subtract again. It's minus 8. Gives us a 0. So whenever you get a 0, it tells you something is a factor. So we've determined the factor. So that's a factor on top and also a divisor. So we have the limit as x approaches to. So for the top part, it's a product of x minus 2 and what's on top, x squared plus 2x plus 4 over x minus 2. So at this point we know this can divide, right? And then what do we have? The limit as x approaches 2. So the only part that's remaining is x squared plus 2x plus 4. And at this point this is easy, you can just substitute, plug in the value of 2. So 2 squared plus 2 multiplied by 2 plus 4. So 4 plus 4 plus 4. Is it 8? No. 12. Alright. So let's now move on and look at some other interesting limits which involve surds. Okay, let's just move on and look at the limits that involve surds. Okay, these are very basic and simple as well. So the limit is x approaches 9 as our starting example, and then root of x minus 3 over x minus 9. So here we know as clearly, if we just try to substitute right away, the denominator becomes equal to 0, so as the numerator as well. So we don't want that. So how do we handle this? So the way we handle this is we want to do away with change the denominator, but we just don't change the directory. So the way to do away with the surd on top is by multiplying by the conjugate, which just requires us to change the sign in between, right? So we're going to have root of x and then change the sign, becomes a positive in between, and then do the same, multiply by the same, the denominator as well, right? Okay, let's move on and see what we're going to have. So whenever I'm multiplying any surd, this applies even to complex numbers. With its conjugate, just multiply the like parts. So I'll multiply the surd part, which is root of x by root of x. So whenever I'm multiplying root by root, the fact that it's x to the power half multiplied by x to the power half, maintain the base at the powers, gives you 1. So the surd is going to disappear there. Okay. So we're going to have the limit is x approaches 9. And then root of x by root of x is just going to be x. And then this part by that part is a minus 9. Over. Now this times that, we just keep it as it is. X minus 9 and then multiply by root of x plus 3. Okay. So I left it for one purpose, just to divide with a numerator to avoid a 0. And then what we end up with is, let me just move this a bit up. So we have the limit as x approaches 9, 1 over root of x plus 3, and then this is just equal to 1 over root of 9 plus 3, which is just going to be 1 over 6, right? Root of 9 is 3, so 1 over 6. That's one we can look at. Very simple, right? Let's look at the limit as x approaches 4. This is very simple. Pause the video and try this one out. So all the same, we multiply by the conjugate. So 2 plus root of x. We're just changing the sign. We'll do the same with the denominator, multiply by the same conjugate. Okay. So multiply the like parts. 2 times 2 is a 4. So the limit is x approaches 4. We have a 4 minus x, and then the denominator part we just maintain. We have x minus 4 multiplied by 2 plus root of x. So we can see that there's nothing we can divide here, but this looks familiar. They look almost like the same, right? So we can pull out a negative from the top part. If we pull out a negative of 1, it means x becomes positive and 4 becomes a negative. So that if you multiply them again, you get negative x plus 4, which is 4 minus x. So that becomes negative 1 x minus 4. Okay. So that you can divide, and then you have the limit as x approaches 4, negative 1 over 2 plus root of x. So you know you have now negative 1 over 2 plus root of 4. So you end up with negative 1 over 2 plus root of 4, that's just 4. Because you have 2 plus root of 4, which is just a 2, so 2 plus 2, 4. So that's our answer. Okay. Now let me add one more, which seems to be the most interesting one to me. So let's have x squared plus 100, and then minus 100 outside over x squared. So clearly, clearly, if you are to substitute the 0 in the denominator part, it becomes undefined. So equal multiply by the conjugate, so root of x squared plus 100. By the way, pause the video and try this one out. So change the sign in between. So do the same to the denominator, root of x squared plus 100 minus 100. So let's do the needful there. We multiply. So multiply the like parts. Whenever you're multiplying the like parts, it gives you whatever is inside there. So the limit is x approaches 0. So we have x squared plus 100 remaining, because these are like, the square root disappears. And then negative 100 multiplied by 100. What does that give you? Remember, you multiply the like parts. So it's going to be negative 100 squared, right? Negative 100 squared, which is which is as good as what? Which is as good as, let me just put square, negative 100 squared. And then for the denominator part, we'll do the same. We have x squared. By the way, this is supposed to be a 10. It's supposed to be a 10. I'm sure you get the idea there. So that it becomes 100, because we just want this to work out. Okay. And then you have x squared multiplied by root of x squared plus 100 minus a 10. So clearly this is going to divide, and then we'll have this and this dividing, giving us a 1. So we have the limit as x approaches 0, and then we have 1 over the root of x squared plus 100 minus 10. So you can now substitute with no issues. So we have 1 over, whatever is x, we're going to put a 0, so it becomes a 0 squared plus 100, which is just 100 minus a 10. Now root of, how is this again? How is this happening? So this is supposed to be, whatever you do to the numerator is supposed to be done to the denominator. So this is supposed to be a positive 10 as well. I apologize for obvious mistakes. Okay. So root of 100 is a 10. So we have 1 over. Root of 100 is 10 plus 10, 20. Okay. So this clearly shows we all make mistakes. So learn from the mistakes, and you can basically check where you made a mistake and just, you know, make sure your answer is right before submission. Okay, let's proceed and look at the limits that involve 0 and infinity. So I hope you guys are familiar with the issue of graphing, because limits also make more sense, especially when dealing with infinity and 0. They make more sense when you look at the graph. Okay, so the basic idea is, if you look at a graph, let's look at the graph. Let me draw the x or y plane so that things can make more sense. So this is what we have. So if I can start with the limit as x approaches infinity, for 1 over x, for example. So how do we sketch this graph? So the way we can sketch is come up with a certain values of x and then plot against the graph itself 1 over x. Okay. So if we try a few values, let's say, let's try -1, 0, 1 to 2. So if I put a -1 where there's x, I'm going to get -1. If I put a 0, it becomes undefined. If I put a 1, it becomes a 1. I put a 2, it becomes 0.5. Okay. So -1 comma -1. So -1 comma -1 somewhere here. And then we have at 0 it doesn't exist. And then we have at 1 comma 1 somewhere there. And then we have 2 comma 0.5, which is like the half of 1 somewhere here. So as you can try 3, you can try 4. I know 4 is going to give me 1 over 0. So 1 over 4, which is going to be 0. Should be 25, I believe. So you've seen that it's going to be getting closer and closer to the x-axis. So the graph will behave like this. Maybe that's too early. So it's going to be getting closer and closer to the x-axis, but it will never cut the x-axis, because the function, it can never be equal to 0. It can never be equal to 0. Okay. So all the same here, if you start reducing the values of x, as you might guess, if you put a 0.1 where there's x there, you're going to get a 10. So the more this value becomes smaller and smaller, you'll be going up and up and up and up. Okay. So how do we determine the limit as x approaches infinity? So in which direction? So we first of all graphed or sketched 1 over x, and now this will help us easily determine the limit value there, right? So the limit as x approaches infinity for 1 over x. So as x is approaching infinity, where is that direction? It's this direction. Okay. So as x is approaching infinity, we know that the value of the function is getting closer and closer to the x-axis. Okay, you may try that, by the way. If you say 1 divided by 100, it's going to be 0.01. If you try 10 to the power 6, it will be 0.0. So we're getting closer and closer to 0. So that becomes the answer. So one comment that I need to make is it doesn't matter what you may have, provided x is approaching infinity and the denominator is heavier compared to the numerator. So meaning that if you can have any constant on top and then just have x raised to any power n, okay, it's still going to be approaching 0. Even if you have x on top as well and then x on the bottom, provided the power of n on the bottom is greater than the one on top, we can call it, let's say, m. Provided n is greater than m, provided the denominator is higher, has got a higher power, this is still going to be approaching 0. Okay, that's very important. Now, I didn't focus on the graphing of this function on the negative part, but all the same, it's going to be more like the reflection. This is what's going to happening. So if you are to look at it as well, as it approaches negative infinity, meaning that as we are going this side, we are all still getting closer and closer to 0. If we do the opposite, x approaching 0, as we are getting closer and closer to the value of 0 in terms of x, as the values of x are getting smaller and smaller and smaller and smaller, we are seeing that the graph is behaving going upwards. It's going up and up and up and up and up. So for us to answer the question, we have to be very careful, because as we approach 0, we're approaching 0 from two sides, right? There's one where we're coming from the negative side, and then there's one where we're coming from the positive side, but we're still approaching 0. Here we are going towards the negative infinity, there we're going towards the positive infinity. So this introduces two aspects of limits which are important. So when you're determining the limit of any value, in this case x approaching 0 for 1 over x, for this to be true, for this limit to exist, as x approaches 0 from the positive direction, for that function should be equal to the limit as x approaches 0 from the negative side. Now from the graph, we saw that this is not actually the case. As we are coming from the positive numbers, in case you've forgotten the graph was appearing, just something like this. So when we're coming from the positive numbers, this direction, getting closer to 0, we are going up and up and up. So that means positive infinity, and then from the negative direction we're going down, that is negative infinity. So these guys are not equal. So since they are not equal, it tells us that the limit as x approaches 0 does not exist. And this is very, very important. Does not exist. Okay. Let's look at a different one. Let's approach it in a case where we have x, right? 1 over x squared instead. The limit as x approaches infinity for 1 over x squared. So I already explained this. Okay, but anyway, let's try to sketch the graph again. So 0, 1, 2, 3. Let's try negative numbers as well. So if you put a 1 where there's x squared, 1 over 1 is just going to be a 1. If you put a 0, it's undefined. If you put a 2, 1 over 2 squared is going to be 1 over 4. So that's going to be 0.25. So something like that. So this is just basically the same one that we had, except this one is moving faster. It's getting to the closer to the x-axis faster because the power is higher. So all the same, as we go up, as you might just guess, it's going to be going up faster. Now this is different compared to the previous one in that if you look at it, in this case, since we've got an even power and then the entire function is also positive, it tells us that we are only going to have a positive y value. So this is the way it's going to behave. so there'll be no negative values to this function. If you try the negative x values, they'll still give us a positive result for the overall function. Okay, so the limit as x approaches infinity, meaning that we're going this direction, you still see that the answer still remains to be a 0. Towards the negative infinity, we're still getting closer and closer to 0. Okay, in short, if you're determining the limit, you're trying to look at what values of y are we approaching as we approach this value of x. That's what a limit is. Now, how do we now look at the one that I'm from explaining? Now, in this case, as x approaches 0. So for this case, the limit as x approaches 0 from the negative side for 1 over x squared. As we are approaching, as the values of x are getting closer and closer to 0, we can see that y is going up and up and up and up, so which tells us infinity. So x approaching 0 from the positive side, what do you think? So it's still infinity as well. So in this case now these two are the same. Since they are equal, it tells us that the limit as x approaches 0 does exist and it's infinity. Okay, so whenever the negative and the positive directions agree, you are confident that the limit does exist. Okay, which we've seen in this case. This is very, very important. So we now have at least ideas on what it means for a limit to approach infinity, to approach negative infinity, for a limit to approach 0. You at least have that background. Now, some of you may be conversant with radical functions. Radical functions are also interesting if we could look at them. Consider a case where we have the limit as x is approaching infinity for 3 minus 1 over x squared. So whenever you have such an expression, what this tells you is, since you've got a negative there, it means you can't have a function value which is going to be greater than 3. They are all going to be less than 3. Why am I saying so? Because if you look at x squared is an even power. It means that this can never change the sign will remain a negative. So for such a radical, just deal with a 3, and you know 3, you can never exceed 3. Okay, so this is where the graph is going to come. It's going to cut at 1. So if we put a 1 there, wait, is it going to cut at 1? Let's try. So for what value, when can this be equal to 0? That's like the question we're trying to answer. So negative 1 over x squared is equal to negative 3. So positive becomes positive. So we have 3x squared is equal to 1. So we have 1 over 3. So it's actually the root of 1 over 3. Okay, so we're going to cut that point, root of 1 over 3. But anyway, it doesn't matter in this case. I was just trying to show you when you're actually sketching. So the curve is going to cut at that point, and then it's going to be getting closer and closer to that. It's supposed to be a bit sharp at first and then slower. So it's not supposed to cut that point. It can never be equal to that, so it will be less than that. So this is the way you sketch a radical function. So when you talk about the limit as x approaches infinity, it means you're looking at x going this side. So you've seen that it's getting closer and closer to 3. Okay? So here the basic idea is, that's the basic idea. The basic idea is, as you're going this side towards the infinity, what's happening? What's happening is, as you are increasing this value, this part is approaching 0 in other terms. So that's the easiest way you can also approach it. Whenever I've got the limit as x approaches infinity, you've seen from the graph that we're getting closer and closer to 3. So the other way you can solve it is by actually distributing the limit itself. Okay, so if you distribute the limit, you have something like as, so pull out the constant, so you have 3, and then you've got the limit as x approaches infinity for 1 over x squared. So I mentioned that whenever the denominator is heavier, you know what to expect. So obviously you have a 0. This is going to be approaching a 0. So therefore the limit is just equal to 3. So a constant stands out whenever you're performing such a subtraction there. Okay. So we can look at several kinds of functions. We can look at quadratic functions. So you know that quadratic functions that have got a positive coefficient of x squared usually behave this way. They face upwards. So how would you basically look at this? What happens is as x approaches infinity, so it means we're going this way. Now, how is the value of y behaving in short? So we're going up, 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 and up. So therefore, whenever x is approaching infinity, we can also see that the value of y is also going up. So it's also infinity. Towards the negative infinity, even as we go towards the negative infinity, the value of x, the value of y is still going up, which is still positive infinity. Okay? So the limit as x approaches infinity and negative infinity, they are both giving us infinity. Now as we approach 0, just substituting the function, whatever you have. So let's say this is what we had. It takes us back to a normal algebraic function, which is just now involve us substituting the value of x. Okay? So you can look at different kinds of functions. The basic idea is just understand what it means. Okay? Now, I can bring more interesting ones. What about if you're looking at an exponential function? So an exponential function cuts the y-axis at 1. This is the way it basically behaves. So on this side, it's going to be getting closer and closer to the negative, to the x-axis. Let me draw it better. Exponential function moves very fast. Okay. Okay. So exponentially, the value of y is increasing very fast. So if you look at the limit as x approaches infinity, in this case, x approaching infinity this way, what would you say? What's happening to the value of y? It's going up and up and up as well, so it's infinite as well. As we are going this side, as x is approaching negative infinity, we're getting closer and closer to 0, as we can see. So that's for an exponential function. For the negative, for e to the power negative x of an exponential function, it's going to be the opposite. It's going to move this way instead. So all the same, you know, since you know how to sketch it, you should be able to determine the values. Now let me look at the inverse of this function, which we call the natural log of x. So the natural log of x is like a fraction of this. So it behaves like this, and then like this. So this is the natural log of x. Okay, it's cutting at 1. So natural log of x. What we have, so for this one, when you're talking about x approaching infinity, you can look at it where is it going in this way. So it's also going up. Okay, so as you increase the value of x, you expect that it's also going to be becoming higher. And then as you go down, as you go towards the negative infinity, you can see, as you go towards the negative infinity, you can see that it's getting closer and closer to the y-axis, but it's going down, so it's going towards the negative infinity of the values of y. Okay, so I think the key point here is, if you understand the way to sketch a graph, you should be able to predict the value of y that is being approached by any given function you may basically have. Okay, now let me add one more, which is very important. The limit as x approaches infinity and then you are dividing. Okay, so whenever you're dividing two different functions and then you're trying to determine the x is approaching infinity, so just divide by the highest power on each part, both the numerator and the denominator. Okay, so for the numerator, what we're going to have, we divide by x to the power 3, which is the highest power for that part. So we have 2x to the power 3 divided by x to the power 3 plus 1 over x to the power 3 as well. We'll do the same denominator. So we'll divide by x to the power 2, which is the highest power. So 2 over x squared plus x over x squared minus 3x squared over x squared. So I already explained that whenever the denominator is heavier than the numerator, that is equal to 0. So what this gives us is we have the limit as x approaches infinity. So this will divide, we have now have a 2 plus 1 over x to the power 3 over 2 over x squared plus 1 over x and then minus 3, right? So we can distribute the limit now. Spare the constants. So we have 2 plus limit as x approaches infinity for 1 over x to the power 3 over, for the denominator as well, spare the constants, limit as x approaches infinity for 2 over x squared plus the limit as x approaches infinity for 1 over x, spare the constants. So whenever the denominator is heavy, as we can see, all these parts will be equal to zeros. So what remains is 2 over negative 3. So what becomes the answer? Negative 2 over 3. So the basic idea, if we go back to the question, is just get the highest, the ones attached to the highest powers of x, and divide them. That gives you the answer. So what this tells us is whenever you're dealing with a limit as x approaches infinity of a normal function, let's say 2x squared minus 1, or let me make it more interesting, the power 3 plus x minus 1. So what this requires you is to divide the entire function by the highest power. So which will give us now, just divide by the power, x to the power 3, x to the power 3, x to the power 3. So you see that only the first part is going to be spared, since the value of x would disappear. Everything else will be equal to 0, equal to 0. So the answer just becomes, and actually, even without misleading or misguiding you, this kind of approach would actually mislead us. But we just apply this concept whenever you are dividing. But when it comes to such an expression, this is a cubic function. So you'd obviously, since you have x already being raised to certain powers, you know that the function is going to be becoming higher, higher, and higher. So it also approaches infinity. Okay. So this is where you'd have to be very, very careful on what you're basically doing. Yeah. So anyway, interestingly, try to sketch this graph and just try to observe what basically happens, what's basically happening to this graph. So we'll now look at the trig limits, trigonometric limits that involve sine and cosine. So starting with sine, so one identity that is important that I want you to know is that the limit as x approaches 0, when you have sine of x over x is equal to 1. So what this means is, it doesn't matter what you have where there's x, provided it's giving you zeros, okay, then this is equal to a 1. So what we want to ensure is, when we have sine of x, or whatever we have attached to x there, if it's the same with what we have on the bottom, then we are going to be sure it's going to be equal to a 1. Okay, so look at a few examples and just apply this same principle. So I hope you've taken note of that, and let's see what we're going to get. So for number 1, let's consider the limit as x approaches 0 for sine of x over 4x. So what do you expect for this limit? What do you expect? So when we look at this limit, we want to have it in the form of sine over x over x. This is the form we want because we know we can't change the x that is attached to a function, sine. So let's ensure we have x on the bottom. So how are we going to do that? So what we're going to do is we're going to multiply by x, the numerator and the denominator. So this will ensure that we're going to have an x on the bottom. So now whenever you're multiplying any trigonometric function, whatever you multiply it by doesn't affect what is attached to the function. So it becomes a coefficient. So therefore what we have on the next stage is the limit as x approaches 0 to b. So we have x sine of x, and then we have x multiplied by 4x. So these have just come on the left. Now on the next stage, we'll maintain the same. The limit as x approaches 0. Now remember the form that we wanted was, we wanted a form where we can have sine x over what? Over x. So we'll remain with that. So let's say sine of x and then over x. So for the top part, I'll pull out again what is not necessary. So the x, I'll take it back this side, and then I'll now also remove the 4x as well. We take it. So we have 4x there. Okay. So now at this point, you know x can divide. You have x there, so you have a 1. On the bottom, you're just going to have 4. So what do we have so far? So let me move back. So the other thing that we know about the limits are, or maybe first of all, let me just rewrite whatever I have. So this is going to be equal to the limit as x approaches 0, and then we have sine x over x, and then we now have, this is a constant, 1 over 4. So the limits tells us we can pull out the constant, so we have 1 over 4. So therefore this is equal to 1 over 4. Now we know that whenever you have x approaching 0 and then x is matching with the bottom, then we know it's equal to 1. So therefore our answer just becomes 1 over 4. Okay, that's a good one, right? Let's look at another one. Now let's consider a case where we have the limit again as x approaches 0, and then this time around we can have sine 3x. Now this time around, we make it interesting, we can divide by another sine function. Okay, so one thing that I want you to know is, when you look at our identity we are using, we are saying if a limit as x approaches 0 and then you have sine x over x, the basic argument here is this is equal to 1. Now somebody may ask, what about a case where we have x over sine of x and then the same limit is applied? Can you say it's the same as well? So the only way to find out is, we know that since that is the case we have, we know that is a reciprocal. So you can take it in this way. To express this in the form of what we have here, it means we're going to have the limit as x approaches 0. So it's like we have 1 now over sine x over x. Now if we know this part, if we apply the limit to the denominator, if we know it's going to give us a 1, right? Does it make any difference if we divide it into a 1? So there's no difference. So that assures us that if we have x over sine of x, we are sure it's also going to just be equal to a 1. Okay. So therefore, applying that principle to what we have, let's ensure that our result will be, we can have sine x, since we have sine x on the bottom, if we can have x on the top part, and then also have sine 3x and then 3x on the bottom, then we are good. So let's see what we can do. So I'll start first of all by dealing with the one having 3x. So we can multiply the numerator with 3x and the denominator with 3x. That will ensure that we have got a 3x on the bottom. And then we can also multiply by x. That will ensure that we have an x on top, as well as the denominator will have an x. So therefore, the limit as x approaches 0 will have sine 3x, and then I'll combine it with that 3x that is coming from that part. So I'll 3x, and then multiply by, and then since I've got sine of x there, let me also indicate it. So I have sine of x, and then I can bring that x there to just combine it. So we've combined the two forms. Now let's not forget about whatever has not been used. So has this been used? No, it's still there. Has this been used? Yes, it's here. Has that been used? Yes, it's here. How about this x on the bottom? No, it's not, so we can have it there. So therefore, at this point we can apply the limit. So the limit as x approaches 0. So we know there the x can just divide, so we have a constant 3. So therefore we have this part is going to give us a 1, so 1 multiplied by, so this part as well give us a 1, and then multiply by 3. So therefore our answer becomes 3. Okay, interesting, right? Now feel free to pause the video and try out this one. The limit as x approaches 0, and then we have sine of x over sine 4x. So you notice that this question is based on the same principle of previous question. So feel free to pause the video and just try it out. So what we're going to do is we will multiply by 4x over 4x, and then x over x. You know I have done that, I've already shown you why. So therefore, on the next step, the limit as x approaches 0. So I can combine them. Let me group sine of x with over x. So sine of x over x, and then I can group sine 4x with that. So it doesn't matter what I start with, but I'll start with the one on top. So sine of x over x, and then multiply by 4x over sine 4x, and then the other part we just have, what's remaining is x over 4x. So on the next step, let's have the limit as x approaches 0, and then I'll distribute it to sine x over x, and then again the limit as x approaches 0, we can have, for this part we can have 4x over sine 4x. I've just distributed the limit to this part and this part. Then the other part, x, that's like gives us like a constant 1 over 4, so it can be pulled out. So now on the next stage, what is resulting is, so we have 1 over 4 multiplied by 1 multiplied by 1. Since we said whenever the x is approaching 0 and then it's matching up, so we have a 0 there is a 0 there, so it's 1. So therefore our answer just becomes 1 over 4. Okay. Now let's look at something that is a bit different from what we've looked at so far. Let's make it more interesting. Let's consider a case where we have a limit and then x is approaching, instead of a 0 it's approaching a 1, and then we have like sine, and then x minus 1 over x squared plus x minus 2. Now one thing that you know is, if you are to substitute in this question we have, if you put whatever we have, you're going to have a 0 there, and then on the bottom was where you're going to have a 0. Now that's not what we want at this point. So we want to ensure that this part matches up with what we have on the denominator for that identity to apply, because what we said is the identity is the limit as x approaches 0. If we have sine of x over x, so if that part is going to be a 0 and this part is 0,
this identity only applies if, first of all, before putting a 0, if what is on top and what's on the bottom is matching up before putting the 0 there. Okay, so let's ensure that's the case for what we have on top. So since we've got a quadratic function, let's consider if we can actually factorize that we have. So I have x squared plus x minus 2. The product there is negative 2. The sum is 1. Whatever factors, what two numbers can you multiply to give you negative 2, and then you add them to give you a 1. So possibly that should be a 2 and a negative 1, because 2 times negative 1 is negative 2, and then 2 plus negative 1 is a 1. So we are sure if we are to factorize what we have on top, it's going to be x plus 2 and then x minus 1, right? Good. So we have the limit as x approaches 1, sine x minus 1, and then over. So we have, so I'll start with this part there by 3, x minus 1, and then I can pull out the other one which is remaining, x plus 2. And then I can just say of is 1 on top. So, you know, that was derived by 3, right? So now we can distribute the limit on the next step, which I'll just do on the same step since I've. So the limit is distributed to both parts, approaching 1. So in a case where they're matching, you know what to do, right? So where they're matching, you know, if you put a 1 where there's x and then there are 1, it's going to be 0. Now the fact that it's giving us zeros and then we are sure that it's matching up, then this is going to give us a 1, because the argument that is made is when you have sine and then x approaches 0. So when you have the limit as x approaches 0 for sine x over x, what this means is, what makes this identity stand is not that x is approaching 0. What makes it stand is the fact that this part and that part should be matching, and then 0, 0. Then it gives equal to 1, we are sure. So we've clearly seen that before substituting, we have this part and this part matching. That's okay. Now after putting a 1, it's also giving us 0 and 0. So the identity stands. Okay, so it doesn't matter what value x is approaching, provided this part attached to the function and the one on the bottom are matching, and then after substituting whatever value you have is giving you 0, 0, then you're good. Okay, now it didn't apply to the first one, despite us substituting having sine 0 over 0. It didn't apply because this and that are not matching beforehand. So therefore this part is equal to 1 multiplied by, and then for the other part we also substitute 1, so you have 1 over 1 plus 2, which is equal to 1 over 3. That's the answer to this question. Now feel free to pause the video and try out this other interesting question. So the limit as x approaches 0, and then sine 3x over 5x to the power 3 minus 4x. An interesting one, right? So feel free to pause the video and try this one out. Alright, so looking at what we have, we can't just factorize this and make it match with whatever we have on top. So we have to be a bit smart about it. So there are two ways you can approach this question. There's what we call Hopital's rule. So there is a video where I'm just going to give you multiple examples about Hopital's rule, and I'll also show you how to answer this one using Hopital's rule. But before I answer it using that form, let's try to look at what we have. So let's try something interesting. Now we know for this to make this easy, we can have 3x on the bottom. So let's multiply the top part and the denominator with 3x. And then on our next step, the limit as x approaches 0, we can have sine 3x, and then we get that 3x there comes here, right? And then the 3x will remain on top, and then this can come down there. So we've just swapped what's on the bottom. That goes there, that one comes here. Cool, right? Okay, so we know that we can factor out an x from that other side. Okay, so let's distribute the limit. The limit as x approaches 0, sine 3x over 3x, and then the limit as x approaches 0 for the other part. So we have 3 over, so we factored out an x there. So on the denominator part, you know that if you factor out x, you're going to have 5x squared minus 4, right? And then on top, you've got 3x. So the x can divide. So you have 3 over 5x squared minus 4 remaining. So at this point, you know this is equal to 1. And then you can distribute an x is equal to 0 for that other part. So it means where there is x, we're going to put a 0, so that part will disappear. So what remains is what? So you have 1 multiplied by the top part 3 over negative 4. So which is just what we got negative 3 over 4 as our answer. Okay. So you can also answer this question using Opto's rule. Opto's rule tells us that if you have the limit of any function, if you have the limit of a function f of x, I don't know, x approaching whatever you have, and then g of x. What this means is the answer is equal to the limit as, even if you differentiate both functions, it's still the same. That's what Opto's rule tells us. So if that's the case, since we know we can't simplify this directly, let's try to differentiate whatever we have. So I've already shown you how to go about differential calculus. So how do you differentiate sine 3x? So sine 3x, derivative of sine 3x. Derivative of sine is cosine. Now you have to multiply by the derivative of whatever is attached to a function. So the derivative of 3x is 3. So that's the answer for the top part. So therefore, this is equal to the limit as x approaches 0. For the top part, you have 3 cosine 3x. And then over, differentiate whatever you have on the bottom. So you're going to have 15x squared minus 4. So that is according to Opto's rule. We've just differentiated the top part and the denominator. Let's try to substitute now 0. So we have the limit as x approaches 0. So you have 3 cosine 3 multiplied by 0 over 15 0 squared minus 4. So cosine of 0, you know 3 times 0 is 0. So cosine of 0, if you know your function, trig functions, this is a cosine function. So it starts at that point. So cosine of 0 is 1. So therefore, you have 3 multiplied by 1 on top, and then the denominator you have, this part is just equal to 0, so you have over negative 4. So which also is equal to negative 3 over 4. So whether you use Opto's rule or use the same normal way of approaching the questions, you still get to the same answer. Now let's look at one more. Let's look at one more to do with sine before we continue and look at the other questions involving cosine. So the limit as x approaches infinity for x sine 1 over x. This is a funny question, a very, very funny question. So it's very difficult for us to answer this question the way it is directly, because the 1 over x is attached to sine. Okay, so well, how do we handle this question? So we handle this question by being smart about it. One thing that we know is, if you have the fraction 1 over x, and then x is approaching infinity, you know that this approaches what? 0. Very interesting, right? We know it approaches 0 because the value of x is becoming bigger and bigger and bigger and bigger and bigger and bigger. So we're getting closer and closer and closer and closer and closer and closer to 0. Okay, now using that argument, we can say let our z be equal to 1 over x. So if we can let our z be equal to 1 over x, what are we going to have? What we're going to have for our limit is, the limit becomes, before I even show the limit, we're going to have, it means, now where there is x, it means we're going to have what? It means we're going to have, if you try to make from that part, if you try to make x a subject, it becomes 1 over z. So where there is x, it means we're going to have 1 over z. And then you have sine 1 over x is equal to z, so you have now z. So it's like we've now changed the function. We've now changed the function. So the limit is now going to be z. Now z is supposed to approach what? Now the fact that if we add infinite there, it means x was becoming infinity. Now that we have 1 over z, which is like the reciprocal of x, it is now 1 over, it's now become the reciprocal, so it's now become 1 over z, 1 over x in other terms. So if you look at this, it means we've now changed the function. So the only way it can match is z approaching 0. It applies. Okay? Because if you say z is approaching 0, if you put a 0 where there is z, it's going to be infinity, which is actually the case for that. Okay? So here z approaches infinity. Or z approaches 0 for it to match up with what we have. So by just us changing or coming up with z, replacing 1 over x, it means we've changed the idea of the entire function, and now the function is approaching, and now z is approaching 0, which can easily help us answer the question. Because this way, it tells us you're now going to have just sine z, so z approaching 0, let me write that property. So z approaching 0, and then you have sine z over z. So this is an identity, right? So it means that's just equal to a 1. Okay, so this is where we hinged with the trig limits involving sine. Let's proceed and look at the other part. So continue and examine the limits that involve a cosine function. So the key important identity is that the limit as x approaches 0 for 1 minus cosine of x over x is equal to 0. Okay, this is a very important identity that you need to know. Now, we need to understand how we get to this point. How do we derive this limit, or how do we evaluate the value of this limit? Okay, so let's remove the 0 part and then see how we can confirm that it's actually equal to 0. Okay, so we'll multiply by the conjugate of the top part, so that will be 1 plus cosine of x, both the numerator and the denominator. Okay, so what do we get? So we'll have the limit as x approaches 0, and then for the top part, 1 times 1 is 1 minus cosine squared of x over x multiplied by 1 plus cosine of x, which if we simplify is going to be the limit as x approaches 0, 1 minus cosine squared of x from the trigonometry, we know that's sine squared of x, over x multiplied by 1 plus cosine of x. Okay, now at that point we can actually break it down. We can have the limit as x approaches 0, and then sine squared of x is the same as sine x multiplied by sine x, and then I can separate the denominator as well. We have the x part, and then we also have the 1 plus cosine of x. So if you're able to remember as we talked about the sine x over x, when you have 0, you know that that part is actually equal to what? So we can distribute the limit. So the limit as x approaches 0 for the two parts, so that we have two different parts of it. So the first one is going to give us a 1, the other one now, if you plug in a 0, sine 0 is 0, and then on the bottom cosine of 0 is 1, 1 plus 1, 2. So this gives us 1 as the answer. Oh, sorry. It gives us 0 because 0 divided by 2 is 0, multiplied by 1, that's a 0. So that's how that identity comes about, and it's very useful when you try to simplify more complex questions. Okay, so let's try to apply it to one question. Let's try to see what we can have. In a case where you may consider the limit as x approaches 0, and then secant of x minus 1 over x, in case I ask you to determine such a limit. So we've come up with two identities already that you need to be familiar with. One that involves sine. Whenever we've got sine of maybe let's say x and then over x, whenever that is 0, this is 0, you know it's equal to 1. Now for the cosine, we've come up with 1 minus cosine of x over x. When the limit is approaching, when x is approaching 0, so 0, 0, that's equal to 0. So these are the two identities useful as you simplify the trigonometric limits. So for this one, we know secant of x is equal to 1 minus cosine of x. So we have 1 minus cosine of x minus 1 over x. Okay. Now we can actually simplify that. What does that mean? When you're dividing by x, it's as good as you multiplying by 1 over x, right? So we multiply the entire part by 1 over x. So end up with 1 over x cosine of x minus 1 over x. Obviously you know that you can't actually get to, you can't substitute pair, because if you are to substitute, it means you're going to have 0 on the denominator part, which we don't want. So how do we handle it? So we know one thing we can do is the limit as x approaches 0, and then the common denominator is x cosine of x. Divide by that, we're going to get a 1, and then divide by this, you're going to get cosine of x. Okay. Now at this point, can we simplify it? How far can we go? So this is now going to be the limit as x approaches 0. We know we can see the identity appearing, right? 1 minus cosine of x, and then we can maintain over x, and then we can separate it with the other part, 1 over cosine of x. And then at that point, you can distribute the limit. So you have the limit as x approaches 0 for 1 minus cosine of x over x, and then 1, and then again the limit as x approaches 0 for 1 minus cosine of x. So for this part, that gives us a 0. Then the other part, you know, if you plug in a 0 where there's cosine, you're going to get cosine of 0 is a 1. So 1 over 1, that's just the 1. So 0. This is how you simplify the cosine function limits, applying that identity that we've derived. Okay. Now when it comes to determining the values of the limits that involve a cosine function, just basically when you say cosine of x, for example, you should be able to just determine the value. Okay. If you've got a calculator just punch in, you only get to apply these other important aspects when you're trying to avoid things like dividing by 0. Okay. So of course there are also aspects of L'Hopital's rule, which I've already explained, that can also help us simplify such limits. Okay. But otherwise, the determinant ones know that the graph of the cosine function begins from a 1 like that. So it continues moving like that. This is how the cosine function behaves. So that's why cosine of 0 is a 1. Cosine of 90 is a 0. Cosine of 270 is a negative 1. And then cosine of 360, is it 360? Actually, this is 180. Cosine of 180 is one that's a negative 1. Then cosine of 3 pi over 2 is 0. And then cosine of 360 is also a 1. Okay. Now, how do you approach the limits that involve the tangent function? I think it is more of just like a comment on how you'd answer. So, very important is how you get to sketch the tangent function. How do you sketch the tangent function? So the tangent function is very funny because unlike the cosine and the sine, this one tends to have breaking points, okay? The lines it can't cut. So we know that you can't determine the value of the tangent of 90, right? It's indeterminate. Because first of all, you know that this is the same as sine 90 over cosine 90. Now cosine 90, we already know it's a 0, so you can't divide by a 0. So this is an indeterminate part. So it gives us a vertical asymptote. So we have something like I'll try to focus on this part. So we expect it not to cut that line. We expect it not to cut this line. So to end up behaving like this. Okay, so this is negative pi over 2 or negative 90. This is 0, and then that's like pi over 2. And again, this continues. Again, from pi over 2 to all the way up to 360. Actually, from to 180. Since you know, so the same is expected to basically happen. Or it's actually going to happen between all the way up to 2 pi. All the way to 2 pi. So, and then this is going to be, so I believe it's going to be something that's going to be like start from here, then again like that. So this is the way the tangent function behaves anyway. So if you are to be asked to determine the value of let's say in this case, what's the value of the limit as let's say x approaches pi over 2 tan of x. So you know that as you approach tan of like pi over 2 from this side, the value is going up, right? So from the negative side, you see that the value, we are going up and up, up and up, so we're approaching infinity. Now from the other side, because again, if you try to sketch the other side, the other part, you see that as you come from the other side, the limit is also different, right? It's approaching negative infinity from the positive side. So this is where we would say the limit doesn't exist. But if you'd consider tangent of 0, you know that it's 0. So the values that you're able to determine the limit, it's easier. So understand, if you know how to sketch a function, it's easy for you to determine the value it gets to approach even as you sketch it. Now, just to give you an idea to what you can just understand what we're talking about. In a case of tan inverse, so tan inverse behaves almost like the opposite. So it has got the horizontal asymptotes as well, the same range of a pi. Okay, so it can't cut this line, it can't cut that line. So expect it to behave like this. So the tangent of this is tan inverse of x. So if you determine the limit as the tangent inverse of x approaches as we approach, let's say x approaches infinity. So we can see as we are going towards infinity, the value of x, the value of y is getting closer and closer to pi over 2. And so that's the answer. So looking at the graph gives you an idea on how you can basically approach determining the values of that function. Okay, so let's discuss the continuity of a function. So if you look at this, we need to determine whether the function is continuous about these different points we have. Okay, but just before that, what does it really mean for a function to be continuous? So I'll just draw before I start giving any formal definitions. I'll give you certain functions. So if I was to give you a linear function, for example, like that, so provided this is just a line continuously, of course I've already used the word continuous, provided it's a line continuously, the function is continuous. Okay, now when I get to make a gap in between, let me try to make a gap in between somewhere, so like that, and then I draw maybe a circle, yeah, small circle like that. So provided there's a gap about that point, if there's a gap, just know that it's not continuous, meaning that there is like a disconnection. Okay, so not continuous. Okay, so if you have equally a curve, if you have a curve as well, provided there's no gap, it's continuous. Now if you find to have a gap somewhere, then you know it's not continuous about that point. You may find that the function may even exist at a different point like this, but the fact is it is still not continuous about that point. Okay, there are other cases where a function may not be continuous, where there's things like an asymptote, right? Okay, so let's say vertical asymptote. So you may have a line like this, and then you've got a function that can never cut this line, for example, and then the function continues again from this other side like this. So provided there is this line as well, we can say about this point or about this line, maybe if x is equal to 2, we know the function is not continuous about that point. Okay, and then finally, one case where we can also have a function not being continuous is this case. You may have a piecewise function like this. Okay, so maybe going the other direction, this is where the function is going, and then starting again from this point going the other direction. So provided there are different points, as you can see, provided there are different points, then you are sure that the function is what? Is not continuous about that point. Okay, so these are cases where function is not continuous. Now let's come up with a definition. So one thing that creates an existence or continuity of a function about a point are three conditions. So number one, so for a function to be continuous, number one is for a function to be continuous about c, about a point x is equal to c, for a function to be continuous, for f of x to be continuous, the conditions that apply are, number one, it means the limit about that point exists. So that means the limit as x approaches c of the function, first of all, should exist. If it exists, that's condition number one. And then number two, the function about that point, let's call it f of x, right? So f of x, which is going to be f of c about that point, should also exist. And then number 3, these should not only exist, but they should be equal. So the limit as x approaches c should be equal to the function about the same point c. So how does this look in reality? So what that looks like is this case. If you look at this function, we have g of x about the point 2. You can see that first of all the limit does exist, okay, and then you can see that the function also exists, so it's continuous about that point. So for a limit to exist, it's also very important to realize that for a limit to exist about a point, the limit as we approach 2 from the negative side should be equal to the limit as we approach again 2 from the positive side. So when these two are equal, then you know the limit exists. So let me give you an example of the point 2. If you look at the point 2, first determine the limit of a function itself, which is x approaching 2 of g of x. We have to analyze the left hand side and the right hand side before the point itself. So the point itself we're talking about is x is equal to 2, which is this line I've drawn. So from the left side, as we get closer and closer to this line, as we get closer and closer to this line, we are sure of one thing, right? We are sure that we are approaching a y value of 1, right? So therefore, from this side, from the left hand side, let me even just draw a normal line. So let me draw a line about this point. So that is the point. So as we are approaching that point from the left side, the value of y is becoming what? 1. So from the negative side it's 1. How about the right hand side? You look at where the function is, how the function is behaving. So we are also approaching 1 as well as we get closer to 2. So this is also 1. So the fact that these are equal and are the same, it means the limit does exist. Okay, that's how you determine the limit. Okay, so if you look at g of x now, since we found the limit, now let's ask ourselves what's the value of a function about that point. So this is 2, so it is shaded at that point, so we know, we are sure the function is 2, 1. So therefore the g of 2 is equal to 1. So you can see now that the limit and the function are the same about that point, and so we are now sure that we have 1. So the limit is equal to the function value about that point. So we can say, we can therefore conclude that what? The function is continuous about that point. So this is where the basic idea, this is what the basic idea of continuity looks like when you look at a curve. Now let me look at the other parts as well. What about if you look at this part? Would you say it's continuous? So the fact that they are not actually about the same point, it's not continuous. We can actually disapprove that by looking at the conditions. So let's try to determine the limit. The limit as x approaches 1 for g of x. So as we approach 1, let's try to determine the limit. So I'll draw a line. So let's try to approach it from the left side. So from the left side, using the function, this is the line. So as we approach that point, we are seeing that the value of y is becoming what? So I'll say therefore the limit as x approaches 1 from the negative side, I can say it's giving 1 as well. Let's try to approach 1 from the positive side for g of x. Let me not forget that. So from the positive side, this is how we are coming closer to this line. So we are getting closer and closer to the x-axis, where we know y is actually 0. So the fact that the negative and the positive side don't agree, or they are not on the same point, it therefore tells us the limit does not exist. So the question actually was asking, find the following limits and explain why they do not exist. So we are saying the limit does not exist because the limit from the positive and the negative side are not the same. So the limit does not exist. So the fact that the limit does not exist, there is no need of us even looking at the function value. Okay, so you can just end there. So it's not continuous, obviously, as we can see from the graph. Okay, so what about if you look at this other point? This is interesting. So by the way, let me make a statement. If you are to be given any point where there's just a continuous linear function, any point where I'm trying to point at that point the function is continuous. So the only points that raise questions are where there's a disconnection or a gap. This is where we've got issues. So if you're to be given a point like 1.5, for example, you are sure that since it's continuous, the line is continuous, so it's continuous, obviously, even without you determining the y value. Okay, now let me give a comment about this other limit. So this one does not exist. This one, it does exist and is continuous, as we saw. Now C, x approaching 3. So I'll draw a line quickly. So if I were to draw a line about this point, let's try to approach it from the negative side. So from the negative side, we are approaching this point, y is equal to 0. So from the negative side, as x approaches 3, from the negative side of g of x, it's giving us 0. From the positive side, we're also approaching 0, as we can see, about the same point, 0. So therefore the limit does exist. So these are cases where the limit does exist against a function value. So this is equal to 0. So we can now go to a second point. So the limit is 0 because from the left and the right hand side we are approaching the same value. Okay. Now number 2. What's a g of 3? What's a function value? So the function value doesn't exist about that point since there's a gap. It is existing at 1. So it's 3, 1. Now this is a case now where we've got both the limit value and the function value, and they're not the same. So the fact that they're not the same, number 3, we can therefore conclude since the limit is not equal to the function value about that point, the function is therefore not continuous about that point. So if you look at the limit of 2.5, 2.5 is obviously somewhere here, so it's continuous about that point, and of course you can try to approximate the value, likely to be 0.5. Okay, so there you're sure the limit and the function are the same about any point on a linear function where there's no gap. Okay, very, very important. Now let me just move on and look at questions that involve no graph. You're just given a piecewise function. How do you answer such questions? So look at such a question, and then we'll look at a few questions that are also just related to us looking at the functions and then just determining whether they are continuous on a set of real numbers.